Again, welcome to DSRT 734 class. This lectures cover scatter plots and correlations. Our main objective is to introduce linear correlation, independent and dependent variables, and also different types of correlation. We're also going to learn how to find a correlation coefficient and distinguish between correlation and causation. So first, we start with the definition. What is a bivariant data? A bivariant data is a data in which two variables are recorded or measured on an entity. An entity can be a person, a product, etc. Now, bi means two. So bivariant means we have a data set with two variables. A very good example would be we have a data set of a company, total expenses on advertisement, and also total revenue for, let's say, 2 years, 3 years. So in this case, we have one data set by two variables, the total expenses on advertisement and the total revenue generated within some specific period of time. Now, previously, we were using univariate. Example would be the scores of students in the class, let's say scores of a test or exams in the class. So again, bivariant data is a data in which two variables are recorded or measured on an entity. Next, we talk about what is a scatter plot. Again, a scatter plot is a graph used to display relationship between two quantitative variables. So it will be a graph. Example would be a graph with X and Y axis. X axis will be the horizontal, Y axis is the vertical. So in this case, we can find the relationship between the X and Y. We can find out if S increased, did Y also increase? Or if Y increased, did X increase or decrease? So a scatter plot will be a graph used to display the relationship between two quantitative variables measured on the same entity again. Now, each data pair may have two coordinates, which we call the X and Y. So every point that we plot on a scatter plot may have X value and Y value. Normally in this case, we may say the S value can be the independent variable, which is the horizontal line, and the Y variable will be the vertical line, which will be the dependent variable. Dependent variable means it depends on the value of X. If X increase, it affects the Y. Or if S decrease, it affects the Y. This means there's a relationship between the two variables. So here we use another term here. Instead of independent variable, we may use the term explanatory variable. And explanatory variable will be on the horizontal axis. Then response variable, which is the dependent variable, will be on the vertical axis. Now, next, what is a correlation? A correlation is what we are going to find. It's a value that will determine if there's a relationship between the X and Y value or the response and also the explanatory variables. So here we say a scatter plot can be used to determine whether a linear straight line correlation exists between two variables. So here we are going to discuss about linear correlation. Also, we have nonlinear correlations such as exponential relationship or polynomial, etc. Here we again concentrate on linear. So a correlation may be a value. So this is a very good example here. First, we have a values on one entity. This entity have two variables, X and Y. We have the X values and we have the Y values. Now we want to find out if there's a relationship between these two variables, X and Y. So we can plot our scatter plot, which is X and Y axis. X is the horizontal, Y is the vertical. Then based on the value, let's say when S is 1, Y is -4. So we can see that when S is 1, Y is -4. The second point will be when S is 2, Y is -2. So when S is 2, we can see Y is -2. When S is 3, Y is -3. So when S is 3, when S is 3, Y is -1. So when S is 3, Y is -1. Then when S is 4, Y is 0. So it's on the X axis. Then when S is 5, now Y is a positive value, now Y is 2. So just by looking at the pattern of the points, we can see that when X increases, Y also increases. And from there, we can determine the strength. So correlation, we have a term called a Psc correlation. Normally, the values will be from -1 to +1, and that would determine the strength of this relationship between the X and Y. So a scatter plot can be used to determine the pattern of a bivariant data set. We also have what we call the inverse relationships. So here we say when there's an inverse relationship between two variables, it means as one variable increases, the other decreases, or vice versa. So we may have increasing relationship, decreasing relationship. Now, this is an example given. We can see in the figure 1, when S increase, Y also increase. But when we look at the second figure, the bottom here, we can see that when S increase, Y is decreasing. So here we will say that the slope of the linear relationship is positive. When S increase and Y increase, it will be positive because when S increase, Y also increase. The second one, the slope of the value will be negative, or we'll say the relationship is negative. Why? Because when S increase, Y decreases. And we are going to determine this by using the correlation coefficient value. So this is another example. Here again, we have an increasing relationship, but not very strong. We can see that in our previous, if we draw a straight line, we can see that most of the points will be on the line. So roughly the R value here will be 1, or let's say 0.99. Here the R value will be -1 or 0.92 or something. But here we can see that when we draw a straight line, all the points will be on the line, which means the top we may have a +1, the down -1. But here, no matter we draw a straight line, all the points cannot be on the line. So this means, again, but when we look at the pattern of the graph, we still have most of the points are increasing, because when S increases, Y also increasing, but some are not. So here the R value will be less than +1, maybe somewhere around 0.5, 0.7, we don't know. And that will be our next section. We're going to learn how to find it. Same thing applies to the second graph here. We can see that the relationship is increasing relationship, but again, the R value will not be +1, less than 1. So here we say the relationship between X and Y is much apparent in figure 4, which is this one, than the top. So just by looking the top graph, I'll say the R value will be positive, lesser value, whereas the bottom, the R value will be more close to 1. At least it will be greater than the top. But again, the R value should be between -1 to +1. When the R value is 0, it means there's no relationship between. So a good example here, we can see that we have a decreasing pattern. Most of the points, when S increase, Y decrease. So the value will be close to -1, but not -1. Let's say somewhere around 0.8, 0.7 negative value. Now, the bottom here may be almost 0. We don't see any pattern here. So this, by looking at this, we will say that the R value will be close to 0. So here we say there's no apparent relationship between S and Y. So that is, here is no tendency for Y to increase or decrease. So when there's no relationship, the R value, which is again the correlation coefficient, will be close to 0. Here we are going to get a negative value. We can see a decreasing relationship. So how do we find the correlation coefficient as we are talking about it? The symbol for correlation coefficient is R. Then as we see here, R value can be any value between -1 to +1. It cannot be greater than +1, and it cannot be less than -1. Now, this is the formula. It will be 1 over n minus 1. N is the sample size. Then since we have two variables, s and y, you can see, when we look at this formula, it looks like the z-score, if we can remember. Z-score, to find a z-score means what? Subtract the mean from each value and divide by the standard deviation. So we do that for the x-axis and we do that for the y value. Then the answer we get for both, we multiply them, we sum it. Now, if the data set is 10 values, x and y, then we may do find the z for x and also find the z value for y 10 times. Then we have the summation, we had everything. So it depends on the n. N will be the size of the data set, how many observations we have. So we're going to see examples soon. Another formula also is given as this. So the computational formula for correlation is as follows also. Again, is the same as this formula. Both work the same way. So here also we have the formula. Now let's see the steps and also an example. How do we calculate correlation coefficient? First, we need to find the sum of x values. So we have the x values. Then find the sum of y values. Then multiply each s value by its corresponding y value. Then find square each s value and sum it together. Square the y value and sum it together. Then we plug all that. So now we have the sum of x, y already. We have the sum of x, we have the sum of y, we have the square sum. So we just plug in all the values and then we find it. Now, the first formula, again, we are going to find the z value for each one. So I'll take the first value, find the z value of it, which means first I'll find the mean of x, the mean of y. Subtract the mean of x from the s values and divide by the standard deviation, which means we need to find the standard deviation also. So to use this formula, the first thing we need to do, find the mean and the standard deviation for both x and y value. Then from there, we find the z-score for each observation, we sum all together. Then we divide by the sample size minus 1. But in this case also, we can find the sum of x and y for each observation. The s and y, find the sum of it, then separately. And then here we plug all the values. So let's see an example. In this example, we are going to use the second formula. So here they say we should calculate the correlation coefficient for the advertising expenditures and company sales data. What can you conclude? Now, our goal is that we want to find out if there's a relationship between advertising expenses and company sales or revenue that they generate. Is it possible that the more money the companies spend on advertisement, the more income or revenue they are going to generate, increase their sales? Well, we don't know. Let's say we are assuming we have this data set from previous years. Let's say each is yearly basis. So first thing we need to do, let's do it very quick by plotting the scatter plot if we want to. Then we can see the pattern, or we just go ahead and find the R value. Now, as we said, the R value will be between -1 to +1. If it's close to +1, it means that when the company spend more money on advertisement, they will generate more revenue. Now, if it's close to -1, it means when the company spend more money on advertisement, it will generate less revenue. Now, if it's close to 0, it means there's no relationship between how much the company spend on advertisement and what revenue is going to generate. There's no any relationship. So here we have the s and y value, which is given to us. First, we sum the x. We also sum the y value. Next, we multiply each observation of the x and y together. Then we sum everything. Then next, we find the square of x and also the square of y. And we sum everything. So we finish. Now, the second formula we are going to use, we are going to plug all the values in. So the R will give us n. First of all, n will be, again, the size of the data set. If we look at it, Since we have 8, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we have 8. So n will be our 8. We also find the sum of xy already, which was 3289.8. We also find the sum of x, which is 15.8. We find the sum of y, which is 1634. So we just plug in all the values. So this is what we did. Again, n is 8 and the rest. After the arithmetic operation, we get 0.9129. That's very good. This tells us that the value is almost close to 1. So if the company spend more money on advertisement, they are going to generate more revenue, or their sales will increase. So here we say that 0.93 suggests a strong positive linear correlation. As the amount spent on advertising increases, the company's sales also increase. Now let's go through the properties of correlation coefficient. The first thing we should know is that the correlation coefficient, the symbol is R. It normally measures the degree of linear relationship, the strength of the straight line relationship between two variables, how well the data clusters around the line. Now, as we said earlier, if all the points are on the straight line, that means if it's increasing, it's 1. If it's decreasing, it's -1. So we say that if the scatter plot indicates a relationship that is not linear, then you cannot use R. Again, correlation coefficient is for linear relationship. Now, the value of R is always between -1 to +1, always. So a value of R near to -1 or near to +1 means there is a tightly bundled around a line, which means there's a relationship between the two variables. Now, if it's close to 0, then there's no relationship. The next thing, we have positive association, which means the R value is a positive value, which means if S increase, Y also increase. In this case, the slope also will be positive. Now, negative association means the R value will be a negative value, which means if X increase, Y will decrease. Or if S decrease, Y will increase. Now, a value of R near 0 means there's no linear relationship between X and Y. And here we say again, it doesn't matter whether you correlate Y with X or X with Y, you get the same answer. What we mean is that if we interchange in the formula, even if we interchange the X for Y or Y for X, it doesn't matter, you get the same R value. Because just by looking at, let's go back to the formula. Just by looking at the formula, we can see S times Y is the same as Y times X. And the sum of X times the sum of Y, if we make it opposite, we get the same thing. Same thing applied to all of them. Now, everything in the denominator with the X's is multiplied with everything with the denominator of Y. So if we interchange it, we get the same answer. Even from the first formula also, the z-scores for X is multiplied by the z-score of Y. So if you change S times Y or Y times X, you get the same answer. Now we say if either variable is converted to different unit, the value of R again will not change. So this is example of few ones we said earlier. We can see based on this pattern, all the points are not on the straight line. So, but we can see there's a very good linear positive relationship. So R is close to 1. Now here we can see there's a decreasing, but there's a little bit space than the previous. Approximately R will be -0.86, decreasing. Here is close to 0. We can see that there's no relationship. When we find R on this point, we get -0.05. Any value close to 0 means there's no relationship. It can be positive 0.2, let's say, or positive 0.05 or -0.05, still there's no relationship. Now, there's a common response here. Here we say that in statistics, a common response normally refers to the phenomena where changes in the both explanatory, that's the independent variable, and the response variable, which is the dependent result from a change in a third variable. We may discuss this more when we cover inferential statistics. Normally, we refer to this term as a confounding variable. Sometimes we may have a situation whereby X shows that S determines Y, but actually, the reason why we have a relationship between X and Y, because there's another third variable, which is, again, we can use the term confounding or locking variable that causes the relationship. Example would be, let's say in Florida, during the summertime, there's a lot of shark attack increases than during the cold season time. But during the summer also, ice cream sales also increase in the beach. Now, this doesn't mean that if a person gets bite by shark, is going to buy ice cream, or if a person buy ice cream, is going to get bite by shark. But again, we have a third variable, which is the temperature that causes the association or relationship between these two variables. So that's why in statistics, we can say correlation doesn't mean causation. We may have two variables that have association or relationship, but one doesn't cause the other. Next, we have what we call the quadratic relationship. Now here, quadratic relationship is a mathematical relationship between two variables that follows the form of quadratic equation. This is non-linear relationship. Now with quadratic, the degree of the equation is 2. If we remember college algebra, for example, s squared plus 2s plus 10 equal to 0 is a quadratic equation. Because quadratic equation, the highest exponent for the variable is 2, which we call the degree. So now the scatter, and we know in quadratic equation, the form will be what? A parabola. Sometimes the parabola may open upward or downward based on the first variable s squared coefficient, if the value is positive or negative. Now, next we say correlation and causation. As we said earlier, the fact that two variables are strongly correlated, or there's association or relationship between two variables, that does not in itself means the cause and effect relationship between the two variables. So you may have two variables that have a relationship, but they don't have no causation. But again, in order to test if there's a direct causation or indirect causation between two variables, we still have to check first if there's an association. Before there will be a causation between two variables, there must be a relationship or association between the two variables. But sometimes we may have association between two variables, but there's no causations. So here we say if there's a significant correlation between two variables, you should consider the following possibility. Is there a direct cause and effect relationship between the two variables? Does S causes Y? Or is there a reverse cause and effect relationship between the variables? Does Y cause X, the opposite? Then is it possible that the relationship between the variables can be caused by a third variable, which we mention as the confounding variable, or by a combination of several other variables? And this will lead us to multiple regression analysis, whereby we may have more than one variable causes the dependent variable, depends on the dependent variable. So here, for example, a simple linear regression concept, we have only one independent variable. We are testing with the dependent variable or the response variable. We may have a concept whereby the independent variable may be more than one, let's say 5, 10, and combination of these variables may determine the outcome. The outcome response variable always must be only one, but the independent variable can be more than one. So here we say, is it possible that a relationship between two variables may be a coincidence? So we need to consider all these concepts. So again, that will be the conclusion of these lectures. In these lectures, again, we cover the concept of correlations and also the scatter plots. Thank you and see you in the next lectures.